If you so your the sampling rate has to be at least how many times compared to the signal's frequency? 2 times at least, but usually we don't do that. Like 4 times or even higher will be better. 2 times is just enough to recover it. I'm going to show you why this is critical. This is a really good example about this. You know, whenever you guys are designing a digital system, definitely eventually everything will be digitized, and you place and all this digital signal or data will be stored in the registers or memory, right? So the interface from analog to the digital world is very important. So we are learning ADC design down to the transistor level, right? Down to the transistor level in the VLSI class. And then here we are learning ADC at the PCB microcontroller level. And in the spring, if you haven't taken embedded systems yet, in embedded systems we are going to learn ADC down to the IPGA level. So a lot of ADCs. You can see ADCs are playing a really important role in this digital and analog electrical engineering world, right? You guys have done that in embedded systems, so you know how that works. So there's an ADC module on IPGA. You instantiate it in your IPGA, then you make the connections to your CPUs. Okay, that's another different way of using ADC system. So after this, you have done a lot of ADC stuff, and it's pretty much covers everything about the ADC, one type of ADC. So if you are in electrical VLSI, we are learning that star ADC block, right? It's called the successive approximation register ADC. And interestingly, so the Arduino microcontrollers are also using the SAR ADCs. It's a 10-bit SAR ADC system. You guys are very familiar with that. So, you know, knowing that VLSI level of the ADC will be very beneficial because one of the registers is controlling the ADC's clock rate. If you don't know what's going on for the clock rate of the SAR block, and you are doing a quiz just after this class for the VLSI class on the SAR, okay? So down to the transistor level, so you know what that clock is actually, how is that clock is actually being used for the SAR, which is very helpful because you will know that it takes more than 10 cycles if there are 10 bits, so it takes more than 10 cycles. It could be 13, could be more, right? Depending on how they design it. If we don't have to make it super fast, it may take up to 18 cycles to get the one conversion done. But it's a commercial product, right? For the Arduino's ADC, it only takes 13 cycles, which is really good, including all the cycles to get all the data available at the SAR block, and also end of conversion clock, and also the door clock, whatever. So eventually, it's only taking 13 cycles for our Arduino's ADC. Okay, and now let's go to the website and look at the first concept to introduce first. You can see a sine wave. For example, we got these red points are the points we sampled. If you ignore all these different sine waves with different frequencies, but just imagine that there are only 6 points being sampled, and then you plug all the numbers in Excel or Python, just let the software to plot it, and there are multiple options. So this big sine wave is not the only option. You can see it might be plotted in different ways with different frequencies. So in that case, you won't be able to recover your actual signal's frequency, and that's a big problem. Does that make sense? So these are the only points available, right? And the plotting software could be Excel, could be Python. It's trying to plot it to recover it. And there are multiple options. You can plot this one, the sine wave. You are thinking, hey, this is the track of the sine wave. We plot it this way. But also, you can also do it this way, right? Just one point, another point, another point. So it's being recovered in different ways. So all these signals are called alias signals of that actual signal. So you have multiple signals most of them are actually not recovering the real frequency. Okay, so that's the issue. That is why we have to use the sample frequency, which is at least twice as much as the original signal's frequency. Okay, it's called Nyquist theorem. But usually we do it way higher, like 4 to 10 times higher than that. Okay? So now let's look at the in class. So you know the first one's answer, ready? Yeah? And number 2. So for the ADC hardware, it's a ADC block already designed by the digital engineers from Microchip. Is Microchip doing well? Is Microchip, the company, doing a good job? Not really, recently. Why? Because all the microcontrollers are easy to be designed or duplicated by other companies. So it doesn't like NVIDIA has a barrier, other people cannot duplicate it. But let's go to, okay, let's look at this one first. So go to this one. Oh, there's a branch in Colorado Springs, I think, or for Collins, for Microchip. You know, they laid off a lot of people. I bought their stock last year and dropped a lot, but eventually recovered a little bit, and then I sold it. So look at this one. You know, when the government applied a tariff, 100% tariffs on Microchip, it dropped like 50% last year. And you can imagine why, because it applied the tariff on China, because the Chinese foundries are making all those chips for them. Why not Taiwan? Why not TSMC? No, why these chips are fabricated by Chinese foundries, not TSMC ones? Yeah, because so for the Arduino Uno is on the 350 nanometer technology. It's super old. You don't have to use TSMC. So TSMC is super good at 5 and 3, and so right overbooked, right, by NVIDIA and AMD for all these high-speed GPUs. But for regular and all these just super general purpose microcontrollers, you just need like something over 180 nanometer technology. It's not running super fast. It's only 60 megahertz. So find out where can do it at the lowest cost, right? But unfortunately, there's a 100% tariff on all these imports from China. Then it dropped 50% immediately. Now recovered. I mean, it dropped to like $50 per share, and then recovered to 70 something. I bought it at the 65. So and then dropped to 50. Right? I was give me a heart attack, and then eventually came back. Right? Usually, you know, for long term holding, if you are holding like NVIDIA ones, it's better. But for these ones, you got nervous because Microchip is not working on advanced nodes. It's usually just 180, and probably some of the microcontrollers are at a 25 or 22, and these ones can be easily beaten by the Chinese companies, Chinese firms. So eventually, if there's some tariffs, and I mean, long-term wise, I think Microchip will just be gone. I think. I mean, 20 years. I don't know. So it's not a long-term thing. Okay. So if you look at the microcontroller over here, so first, as we have learned, right? So usually we set up a reference voltage for the ADC or DAC, and that defines the range, and then we divide it by how many bits of the resolution or how many steps are in there, depending on the resolution of the ADC. So what's the resolution of this ADC over here? What's the resolution? To the 10. So no, 10 bits. You should only answer 10 bits. If in the interview, the people ask you, hey, what kind of ADC have you used, right? And you told them, I have used the 10-bit ADC from the Arduino microcontroller. Okay, what's the resolution? 10 bits. That's the only answer you wanna give to them. Okay, but nothing else. So 10 bits will be the resolution. Standing answer to that question, and definitely there will be 2 to the 10th of steps to resolve that whole range. So what's the voltage to define the range of the ADC? Go back to the tutorial here. You can modify it. Look at this table. So what's the register controls it? It's AD mux. It's multiplexer. And you have 2 bits. It's a reference 1, reference 0. There are 2 bits, so I have 4 options to change the reference voltage of the ADC. Okay, so the 00 option will be AREF. So what is AREF? AREF is over here. That's the pin of the microcontroller, and you can see I don't connect this one to anything else, right? So I'm not connecting this to anything else. So which means I'm not using mode 00. You can see mode 01 is AVCC. AVCC. Do I have anything to AVCC? Yes. So the VCC is shorted to where? To where? To the supply voltage, 5 volts. So 5 volts is the reference voltage for this ADC for us to use, and you can see what's the smallest voltage can be resolved or can be detected by this ADC. You can do the calculation. How to calculate it? It's 5 over 2 to the 10th. I mean, what is 2 to the 10th? 1024. This is something we need to know. It's common sense, right? You don't have to run any calculators. What is 2 to the 8th?
256.
Yeah. Okay? You have to know. And AVCC is shorted to the power supply, and you know that it's going to be 5 volts divided by 1024. It's very close to 1,000. 1024 is very close to 1,000. So you can quickly calculate that. The smallest voltage can be resolved by this ADC will be very close to, what's that? 5 millivolts. That's the answer I want to hear. Okay? Don't let me know 0.005. No, that's too lame. Don't say that. Okay? You guys are experienced electrical engineers. 5 millivolts. And it's also asking, hey, AVCC, the reference voltage, and also you want to connect a capacitor to a ref. But we don't have a capacitor to a ref. Is that okay? It's not ideal. That's a Skyboard version, Skyboard version 2, so we don't have it. All right, but you know, if you connect this one to a voltage, then you probably won't be able to use other. You know, it's for example the first mode. Okay, it's the first mode. It's using a ref, so you are supposed to connect the voltage to a ref. And for the second one, AVCC, and you need to put the capacitor at a ref, because for the second one, you are using AVCC as the reference voltage, and you don't want to use a ref pin, the input from there, as a reference voltage. So that's why you either leave it disconnected, or you put a capacitor on it. And a capacitor is just a low-pass filter to get rid of any surges. So in that case, you got a really stable 0 over there. It won't affect anything, because the microcontroller, if it detects a ref had the certain voltage, it won't let you use the reference voltage from AVCC. It's just confusing it. So that's why you want to put a low-pass filter on it to get rid of any surges, or just give a steady 0 to it. So mode 10, it's going to be internal 1.1 volts, and mode 11 will be internal 2.56 volts. What are the purposes of using these two reference voltages? Can you think of? Why we want to use smaller references? What are the situations we want to use smaller references? Could you change the resolution of the ADC? What's the resolution of the ADC? 10 bits, right? So can you change the resolution? No, right? If you want to increase the small or decrease the smallest voltage to be detected, all right, what you can do?
You can do it across 1 volts.
Reduce the reference voltage. It's gonna be like 1 volt divided by 2 to the 10th. We'll give you like 0.1, or we'll give you a 1 millivolt as the smallest to be detected, depending on your application. All right. So for example, there's a sensor you know. It could be an analog temperature sensor. It could be analog humidity sensor. Is outputting like 10 microvolts, and you only have Arduino's ADC to be used. What you can do? 10 millivolts output from the sensor. But the smallest voltage you can detect from here is about 1 millivolts. But that's the 10 microvolts change that you have to resolve. So there will be a sensor, here's the ADC. What's in the middle? What's in the middle? God. Box, G-O-D, right? So make it happen, please. What's in the middle? Amplifiers, right? Amplifiers. You want to amplify it to the range. For example, now, if you are using this one, right, because you want to resolve it better, so you have a 1.1 volts range. So when you amplify it, in the amplification, usually we call it pre-amplification. What's the gain is desired for the preamp? Yeah? Can we do 10? Can we do 10? What's the problem with doing with using a 10 amplification over here?
It's not going to make the full range.
Yeah, so you have overall you have 1.1 volts, right, as a range, and you want to amplify it until the point that it's very close to the whole range. So you can utilize the whole resolution of it, right? If you just amplify it a little bit, this is the original signal, amplify a little bit, you're losing a lot of leverage over design. So what's the common amplification per stage, and why? For example, we want to use 100. Okay, what's the common? So how do you want to? Would you like to use one amplification with 100x gain or multiple stages, and how many stages usually? No more than 20, depending on the quality of the amplifier, but usually 5, 10, but no more than 20. When it's getting closer to 20, you should feel nervous about it because it's going to amplify the noise as well, so eventually are eating up your resolution over here. So for this one, how many stages would you like to put on it? It's a trade-off, right? Put more stages, it's better performance, but however taking a lot of footprint. So how many stages? 2 tens, right? Another like this. Right? Just some side note over here. So we want to use AVCC, so I have to set up ref S1, S0 to be 01, and you want to connect the capacitor to it. But to accommodate all different modes, what kind of improvement you can make to the schematic, to the design? Think about it. Because sometimes we need to use AREF, sometimes we don't need to use AREF and want to make it more flexible. And you can see that AVCC, I don't know if you have AVCC there and you want to use AREF, which one will be used eventually. If you put a 0-0 mode over here, but still have a voltage at AVCC, is it going to take AVCC or AREF, right? So that's my question. So what's the best way to deal with this? Just have 2 header pins, right? You can put a jumper on it if you want to choose this mode. So if you are a teacher, you can write it into the tutorials, take a picture and circle it. If you want to use this one, put this jumper on it, right? So just disconnect all these connections, and on the other side of the connector, and label it. Okay. So whenever you want to use it, you have a flexibility to just put a jumper on. All right. Some side note over here, and so that answers number 2. For number 3, how many bits are in the converted results register? So which register is holding the result? Let's look at the first one. So how many bits are there in the ADCHL register? How many bits? 16? Is that 16? No, 10. See, these upper 6 bits are not used. So I have 2 bits. I mean, more bits will be more resolution. It's more helpful, more information. However, all these registers it's an 8-bit microcontroller system. So all the registers are 8 bits. So if you want to hold another extra 2 bits, you need a different register. That's why it's using 2 registers to hold the 10 bits, right? But you have 2 options. You can, if you place a 0 to this bit, ADLAR, this bit, then it's write justified. You know what I'm saying? So all the result 10 bits are shifted right, justified to the right hand side. Because you can see here ADL, ADCL, the lower byte is holding starting from the LSB. And then here's the two bits over here. However, these are just registers, and the registers stores binary values, so these are basically just 0 and 1s. Okay? If you really want to use the entire 10 bits, you have to shift these 2 bits or the result from ADCH to where by how many bits? Where? So let me ask you a question here. So this bit over here, 1, if I put a 1 here, it represents what? To the 8th. So if you want to recover these 2 bits, so you got a 1, 0, 0, 1, whatever. These are just 2 binary numbers, right? If you want to recover it into its real value that they represent, and you should shift these 2 bits to where by how many bits? Very quick question. So after the conversion, ADCH register will hold 2 bits. Okay? However, you don't want to directly use these 2 bits. You have to do this. Shift to where by how many bits? And this has to be what? Unsigned int 16 type, right, for result.
Is it left by 6?
Left by 8.
Why 8?
Why 8? Because this bit over here is for this register is being stored at the LSB only represent 1. You have to shift it. So imagine it's over here. Have to shift it by 8 bits to move it to the, like, you know, this is 1 byte, it's another byte. You shift it to the left by 8 bits. You're getting these 2 bits over here, right? So
Can't see it.
and now they so shift it by 8 bits. They were here, right? So by 8 bits it becomes here, and this one represents 2 to the 8th. So result, this is the result register, right? And that register is a 16-bit register. Any question on this? Okay. So if we give ADLAR a 1, you're right justifying that or left justifying that? If you give ADLAR a 1. Left. Okay, so this option over here. All right. I mean, I still like this classroom, even though sometimes you guys are getting confused. I'm losing some of you guys, but still I can tell it's almost 90 to 100% of you guys are paying attention to it, at least, right? So for other schools, I taught 100 students in the classroom, only 20 of them sitting in the front rows are paying attention and looking at me. All the other people, you can tell they are doing something else. And I still remember, I mean, that was, I got shocked because the people were just sitting back there, and a girl was just looking in the mirror, and when I was teaching super important things, I got super disappointed. I couldn't really teach in that classroom anymore. I like here a lot. You guys probably don't know because this is the college, the first college or the only college you have attended. But other bigger schools are so different, so different. Like he was in CSU. I mean, it's a lot of times you are forced to do things that to keep it consistent across all the sections. And if they don't allow you to do quizzes or do this kind of in-class things, and other professors they're lazy, they don't want to grade it after the class, they won't do it. If I'm not doing this, who cares? You guys will be just zooming out, right? It's Friday, I'm gonna do something after this, right? But now you care about it, you are paying attention, you are writing answers on it. I think that's good. That's why I love teaching. Love teaching here, not anywhere else. You guys are awesome. You guys are awesome. All right, AD, LAR, give a once, left justify, and there are some tricks about this. So usually, definitely, you can read both registers and combine them as a 16-bit data, of course. But that increases the complexity because a lot of times we're looking at the data by what? Serial. Okay? By the serial, UART. And UART is transmitting how many bits? 8. Okay? So if you have to transmit 16 bits or 10 bits, you have to do one first and another one, and then you have to do a lot of coding over there and combine them, receiving them and combine them afterwards, right? So that increased a lot of complexity to our coding. So what can we do is we just drop the lower 2 bits. Would you like to drop the lower 2 bits or higher 2 bits? Lower 2, why?
Because they're the least significant.
The least significant, yeah, that's why the name, right? The name makes sense. They're the least significant bits. If you drop them, you're just losing a little bit of resolution, okay? For this application, it's probably fine. So if you drop the lower 2, you are keeping the higher 8. Okay? My question for you guys is, because after the conversion, the converted data will be stored in ADCH and ADCL. If you want to directly just read it, can you directly just read from ADCH? Do you need any shifting or anything? Combination, shifting, and anything to ADCH for ADR1? No. Why? Why do you have to shift it? You only need the 8 bits, the higher 8 bits. And for this option, it's already stored in here. Can you just directly assign ADCH to a variable or the final result you want to hold it? Do you have to shift it? The answer is no, it's already there. It's 8 bits, it's already there. You just directly use it. You just drop the lower 2 bits. Don't do it. Don't use it. Confusing?
Well, you could, I mean, yeah, you'd have the same binary number, but it wouldn't be representing the same value until you shift it, right?
It stores. So these are just binary numbers, right? Just binary numbers.
If you just take ADCH straight out, then like
Yeah.
the most significant bit is going to be representing 2 to the 7th instead of what it should be 2 to the 9th. So you
I
still
think-
have to shift it before you actually use that value.
Yeah, I think yeah, that's a good question. Let me see. So the number starts from LSB over here, right? These are just the bits. If you align the bits together for 10 bits, these are just numbers. Right? These are just numbers. Let me think about it. Do I need to shift it by 2 bits to the left?
If you want to.
It's possible, right? It's possible. I have to take a further look at it. That's a good question. I was thinking about it's just direct the results from that one. I think you should probably.
If you were just gonna like print it out immediately,
Yeah.
you wouldn't get the value that it's actually those bits are actually supposed to represent.
Yeah, let me
It's
confirm with
just
the data
for
sheet.
purposes.
It depends on how they design it, right?
It's
If we
just-
keep it consistent, if you doing similar things like what we did over here, seems like we should, because this bit over here doesn't represent 1, it represents 4, right? So in that case, we directly use these binary bits we're actually pretending this one is a 1, not a 4.
Uh-huh.
So it makes sense if we probably should shift it to the left by 2 bits. I think that's the case, but let me confirm with the data sheet after this, okay? I think that's the case. So if you don't shift it, you're actually dividing your result by 4, right? Okay? So that's so question number 3, right? How many bits are in there? The 10 bits, and when ADCR is 1, how many bits are stored in ADCL? 2, right? That's 2 bits. So what if only ADCH is saved as a final result? That's fine because it's just reducing the resolution a little bit, right? It's fine. We can directly use the ADCH value without using the ADCL at all. Okay. So the last one is a little bit trick over here. Could you just read ADCH since you just need ADCH? Could you just read it and never mention or never read anything from ADCL at all?
If ADLAR is 1.
But the answer is no, you cannot. It's the digital designer in Microchip that designed it that way. So you have to read ADCL first and then read ADCH, even though you don't need ADCL, but you still have to read it. So which means you have to write that line and put ADCL on the right hand side of the equation and assign it to a variable, and even though you don't use it at all. But you still have to do it at a certain sequence. You cannot read ADCH first and then read ADCL and then you just use ADCH. Nope. You have to read ADCL first and then read ADCH and then just use ADCH. Does that make sense? You have to follow that sequence because that's how it's designed. So just have to follow that sequence, right? Number 4. In the ADC control status register A, ADC SRA, which is this guy, which bit enables ADC? Super simple, you can tell, even from the name. You can see this register. Oh, where's that register? Here, right? This register. Which register enables it? Aiden. Just kidding. Right? Number 5, in the same register, the mode ADPS2 to ADCPS0, there are 3 bits to control the ADC's input clock. You're in VSI, you know what that means, right? That clock controls the start block's clock. Okay? Because shifting that sequencer on the top. So 101 will give you what kind of frequency or input clock to the ADC. Where is that register? It's am I losing it?
Below the waves.
Below. This guy, right? 101. 101. 32 per scalar. So what's the input clock? Input clock to the ADC. 16 mega divided by 32. Okay. What's the frequency over here if we do that? I think there are some calculations. So it's gonna be this guy, 500 kHz. Is that the sampling frequency or not? Why? Is the sampling frequency? It's a clock to the ADC. To where? To the SAR blocks sequencer. Or in VLSI, right?
So then there's 10.
Yeah. At least a 10, right? But actually it won't get 10 because you need a end of conversion in the door kick. You need several things. So how many clocks are required to get a conversion done? Usually 13. So after 13 clock cycles, the data will be ready. So your sampling rate should be lower or higher than that.
Lower.
Mm-hmm. Lower or
You
higher
divide it by,
sampling
like,
rate.
13. That'll be your sample rate.
Should be lower, right? Because this has to be ready first. So that when the 13 cycles is done, the conversion is done, the data is available.
Sample.
Then you sample, right? It's like
13 clock cycles. per
yeah,
sample.
13 clock. Yeah, that's the ideal case, but usually you want to slow it down a little bit, right? And you don't want to directly use that. So for the calculation here, let me draw a diagram really quick. So the way we handle the sampling is to use ISRs. So whenever it enters, so we use a timer to control it. And whenever the timer triggers it, it goes to the ISR and sample one sample. Okay? And when the sample conversion is done, it triggers another ISR and you store it. So that's where you'll do the ADCH assigned to your variable thing. Think about it. How many ISRs we're doing here, we're using here? How many ISRs? Two. The first ISR controls the sampling frequency. So it enters that ISR. See here. That's conversion ISR. It enters this ISR according to your sampling frequency, which you doing here is 25 microseconds per sample. And could you calculate that really quickly for me? For 25 microseconds per sample, what's the sampling frequency of that? 4K, 40K, 400K. Which one? 40K. 40K. So whenever it enters this ISR, it does what? Only one line. Only one line. So I'm doing a testing. I'm pulling it high and then pulling it down just to measure if I'm doing a 25 microsecond sampling from the oscilloscope. But these are just the testing pins. Don't worry about that. But actually, there's only one thing is being done, which is start the conversion. So whenever it enters ISR, it starts a new conversion. Okay, so you can just do everything here like until the because the ADC also has an interrupt. So whenever the conversion is completed, it will interrupt. So you can look at the flag and decide if you want to do it here. But however, keep in mind, you don't really want to put a while loop, a dead loop with a semicolon inside the ISR. You don't want to do a dead loop in the ISR. That's a good practice. Don't do it. Okay. So what you want to do is use another ISR to detect the completion of the conversion interrupt of the ADC. Can you imagine the process? Think about it. The 25 microseconds interrupt only starts the conversion. Okay? Only starts the conversion. And then, when the conversion is done, it takes 13 cycles at least. It will trigger the completion interrupt of the ADC and run this part of the code. So this is where you handle it. See, I have to read ADCL first to follow the sequence, and then I read ADCH. But eventually, I only use ADCH, but you still have to read ADCL. That's from the design of the microcontroller. Still have to read both, but you only store ADCH. Okay, you read it, and then you do this, and you store only the high byte. But according to the discussion just now, we probably need to shift it to the left by two bits to make it accurate. But I'll confirm with you guys next week. Don't worry about that. Okay, and then you increment the index. if it's already done, then stop the timer and turn on the flag, set the index to 0. And so keep in mind, you need 2 interrupts to do it. 2 interrupts to do it. So if you look at the diagram over here, let me see. Your ADC interrupt (25 microseconds for the interrupt, right? Every time you interrupts over here and get into the do one sample. So the sampling and conversion time should be shorter or longer than this guy. It's 25 microseconds per sample, right? Just keep doing this. Just keep doing this. So the ADC conversion, that time consumed over there should be shorter than each block or longer than each block. Shorter. Okay? So it interrupts the conversion. Conversion is done, right? And trigger a second interrupt into the conversion. It has to wait until it finishes the 25 microseconds first. Even though conversion is done, it triggers that ADC completion interrupt, and that one is not timed because whenever this is done, it will do that, right? Do the ADC. And that one is really fast. So all the code over here, just several lines, will be executed really quickly. Definitely will be less than this guy. So it's actually doing, so once this is triggered, it starts a conversion, right? So once this interrupt is triggered, it starts a conversion because that's what we have over here, right? Starts a conversion, 25 microseconds, right? It starts a conversion, and it will start doing this. Whenever it's done, trigger that ISR for the ADC completion over here, right? Because the data is available, and do it. Okay, and then what? Then it goes to where? Let me slow down a little bit. Am I losing anybody? Slow down. Don't worry about that. It's the first time you guys are doing this. I've been thinking about and going through this tutorial through a lot of troubleshooting for many hours. So it's the first time I'm introducing this to you guys. Let's slow down a little bit. So 25 microseconds ISR for the sampling rate. Easy, right? Easy to understand. No problem. So every 25 microseconds is going to trigger which interrupt over here? Which one? Top one, bottom one? Top one. Okay, top one. So it's controlled by timer 1, which is a 16-bit timer. So it's going to trigger this one. And trigger this one is going to do what? Do the conversion. Start a conversion. Okay? Start a conversion. But nothing else. It's not doing anything else. Just start it. Just start it. If I draw an arrow here, it's going to start here. Is that accurate? Start a conversion whenever it enters the ISR. Start a conversion when it enters the ISR. It's accurate. It's okay. Just starting here. And then what? We'll do the conversion, right? It takes time. And then whenever it's done, doing what? Trigger which ISR? The second. So that's called the ADC completion ISR. There's a flag. We're not handling the flag, because the ISR will automatically clear the flag by itself. So we don't have to touch it. That's a good part of the ISR. We don't even need to know. It just enter ISR after it's done, it clear it. You can also handle it by yourself if you don't have ISR. Okay, you can have like ADF. I think the name is ADCF1 or something. You can always check that flag. It's called polling, right? Polling. In an interview, you can tell them what kind of things you are doing. You can polling a flag, right? You can polling a flag, or you can just use ISR. Okay, either way. So ISR will directly clear it, and whenever it's done, it should be here. It's not finished. So this should be shorter than 25 microseconds. So done is over here and do this completion. You store the ADC edge. And then what? After this, then what? We'll stop this one earlier or what? Can you stop this earlier? No, it won't interrupt again until until it reaches 25 microseconds. It only interrupts every 25 microseconds. Have to use all the time over here. It just jumped to here, and then what? Oh, go to where? Go back to here? No, I mean just at this moment, it will go back to where? After this is done. Because this is really short. This can be done like within this time frame. Then what? Go back to the ISR over here? It will go back to the loop where it interrupts. Go back to the original position in the loop. All right, do whatever over there and wait. I think it's just a while loop, just waiting there, and then until the 25 microseconds is done, then we'll interrupt another conversion. Okay. So for the conversions, the time being used for the conversion, you have to be very careful about it. So here are the calculations. Let's look at the Implex 11 first. So we are at number 6, right? The number 6. No, number 5. We just finished the number 5. Number 6. What's the common human whistling frequency? It's 2 to 4 kHz. I googled it. 2 to 4 kHz. It's important to know, right? It's important to know. You have to know the input signal, what's the frequency of it, then you can choose sample frequency. So for 25 megahertz, we just did a calculation. What's the sample frequency of that? 25 microseconds per sample. What's the sample frequency? 40K. Is that way larger than 4K? Yes, this is good. It's good enough. Okay. Then I think the next task is just to choose a good conversion time, right? So we have a prescaler there. Why we have to pick up different ones? You can see from here. You can tell. Definitely, you can use a faster one, but the thing is, the faster one will give you compromise the accuracy of the conversion. So you can tell that until a point. We'll do the calculation next time, but until a point, you keep changing, you keep making it faster. If you look at here, you can make the conversions this much, this much, this much. So until a point, you won't have aliasing anymore, so it should be fine. But it's getting a poorer and poorer accuracy if you do it really fast. Okay, so that's why we want to keep it just about right. So we're not compromising the accuracy, but also it's less than 25 microseconds. So we'll do the calculation on Monday, but you can tell that I'm showing you these results over here. So until a point, I'm giving this prescaler of the ADC's input clock to 100. I change it to 011, use a small prescaler, and then a smaller prescaler will give you a faster conversion rate, and then faster. The frequency is not getting really changed. I can always recover my whistling, or the video audios of whistling. You can see the sound waves. It's not changing too much, right? However, if you use a different conversion time, aliasing. Does that make sense? It's the same whistling. It's a problem. So that's a very important thing to consider when you are designing an ADC system. The analog signal, sampling rate, ADC clock, input clock. So there will be quizzes or a problem on the exam about designing ADC system regarding the input frequency and everything else, okay? The registers. So you are engineers, you need to design everything from scratch. Okay, we'll keep talking about this on Monday, right? You don't have to turn it in. We never finished it in class. Next time I'll name it as in dash out class.